In exercise 9.1, we're looking at hydrohalogenation, so adding a hydrogen and a halogen, hydrohalogenation, hydrogen, and a halogen onto a double bond, but we're looking at it from the perspective of synthesis, so we're not thinking about the mechanism necessarily, we're thinking about hopscotching from the reaction to the product. So if they just give us the reagents, what product should we predict that we would have? Okay, well there are two options here. We know we're adding H and X. We know we're adding hydrogen and some halogen, and we're going to be adding those onto the carbons in the double bond, provided that there is not a carbocation rearrangement. And these are different things, the hydrogen and the halogen, so we have to think about where each one goes. And there are two options here. We could either have Markovnikov addition. That means that the hydrogen will go to the hydrogen will go to the less substituted carbon. Or you could have anti-Markovnikov addition. That's where hydrogen would go on the more substituted carbon. And you'll recognize anti-Markovnikov addition because you'll have a peroxide. So that's a molecule that has a lot of oxygens in it, two oxygens bonded to each other. Watch out, rearrangement is possible in here. That's something we always have to think about because if you think back to the mechanism, you form a carbocation. Okay, so just in terms of drawing the product, what steps should you think about? Well, when you see hydrohalogenation, and you'll recognize it because you'll have an alkene and an HX, where X is one of the halogens, fluorine, chlorine, bromine, iodine. You'll see that, when you see that, just redraw the carbon skeleton, but without the pi bond. So all the sigma bonds are going to be exactly the same. We're just changing the pi bond. We're taking the pi bond away and using those electrons to stick a couple new things onto the molecule. So redraw the carbon skeleton without the pi bond. Okay, now you want to identify the two carbons that you're going to add your H and your X onto. Well, we know that the H gets added to the less substituted carbon. We know that because here there are no peroxides, so this is Markovnikov addition. We don't see ROOR, like over here. We don't see that. So it's Markovnikov addition, so the H is going to go to the less substituted carbon. This carbon here, of the two carbons in the double bond, this one here is bonded to 2 carbons, so that is secondary. And the other carbon in the double bond is bonded to 3 carbons, so that is tertiary. Because this is Markovnikov addition, the H will go to the less substituted carbon, the secondary one. So that's where we'll draw that H in. And then the other thing, in this case the halogen, the bromine, will go on the more substituted carbon. You just have to watch out, because at first in this mechanism you form a carbocation and you have to think about whether that's going to rearrange. Now right now it's on a tertiary carbon. Each carbon next door is either secondary to the left and right or primary above. So there's no reason for that carbocation to rearrange. It's already at the most stable position it could be on. And so that's what the bromide is going to attack, and that's where the bromine will attach. And so that is your product for that hydrohalogenation. Okay, let's go through the same procedure for a few more. So in B. Now in B, you see the two signatures for hydrohalogenation. You have an alkene and you have an HX, where X is one of the halogens, fluorine, chlorine, bromine, or iodine. And when you see that, immediately draw the carbon skeleton exactly how it is, just without the pi bond. Okay, and we know we're going to add an H and an X onto the 2 carbons in the double bond, so these two. But we have to think about where they're going to go. Now we see an ROOR. That is a peroxide, and that's a sign that this is going to be anti-Markovnikov. If this is anti-Markovnikov, then H will go to the more substituted carbon. So we think about the two carbons in the double bond. This one on the right is only bonded to one other carbon, so that's primary. The carbon on the other side, this one, is bonded to 1, 2, 3 other carbons, so that is tertiary. So this is the more substituted carbon, and that is where the hydrogen goes in this anti-Markovnikov addition. Now, when you use peroxides and do the anti-Markovnikov addition, the mechanism is actually completely different from when you don't use peroxides. So actually, in this case, you don't form a carbocation, so you don't have to think about rearrangement if you're doing this anti-Markovnikov addition. And you don't have to know the mechanism for how you do this hydrohalogenation in the presence of peroxides for this chapter. You do need to know the mechanism when you're doing hydrohalogenation without peroxides. But for now, we see a peroxide, we know it's anti-Markovnikov addition, the hydrogen goes to the more substituted carbon, and the other thing we're adding, in this case the bromine, that's going to go to the less substituted carbon. And so that's our product. Okay, let's try it with another one. So we see the signs, we see an alkene and we see an HX, a hydrogen and a halogen. So those are the signs that we're going to do a hydrohalogenation. So we know that all we're going to change is the pi bond. You can redraw the same carbon skeleton just without the pi bond. We're going to look at the two carbons in the double bond. Okay, well, if we look at the recipe for this, we don't see a peroxide. We don't see ROOR, so that means this is Markovnikov addition. That means that the hydrogen will go to the less substituted carbon. This carbon here in the double bond is bonded to 1, 2 other carbons, so that is secondary. The other carbon in the double bond is bonded to 1, 2, 3 carbons, so that is tertiary. So the hydrogen is going to add, because this is Markovnikov addition, the hydrogen is going to add to the less substituted carbon, that is this secondary carbon right here. So we're going to put the hydrogen there, and because we're not using peroxides, we do form a carbocation here. The carbocation will form on the other carbon in the double bond, and we have to think about whether that's going to rearrange. So it's on a carbon that's tertiary already. There are secondary carbons above and below, and a primary carbon to the right. So it's already on the most stable position. It's already a tertiary carbocation, so it's not going to rearrange. And that means that the bromine will add on that carbon where the carbocation was. The negative bromine is going to attack that electrophile. And so that would be our product. Okay, let's try another one. For D, so we see a double bond, an alkene, hydrocarbon with a double bond, and then we see a hydrohalogen, a hydrogen and a halogen. Remember, the halogens are fluorine, chlorine, bromine, or iodine. So that means we're doing hydrohalogenation. We're adding H and X. Now, we don't see a peroxide. We don't see ROOR. So we know that this is going to be Markovnikov addition. The hydrogen is going to add to the less substituted carbon. Here, this carbon at the bottom in the double bond is bonded to 1, 2 other carbons. So notice we're only paying attention to carbons in the double bond. So we have, that's secondary. And the other carbon in the double bond is bonded to 1, 2, 3 carbons. So that is tertiary. And so, in this one, the hydrogen is going to add to the less substituted carbon. That's the secondary one. So we'll redraw the carbon skeleton just without the double bond. And the hydrogen will add to that less substituted carbon. The chlorine may add to the other carbon. We have to think about whether that's going to rearrange. So we'll form a carbocation there. That's going to be a tertiary carbocation. That carbon is bonded to 1, 2, 3 other carbons. So tertiary. Next door we have primary, secondary, and secondary. So that carbocation is already on the most stable position nearby, so that won't rearrange. That means that the chlorine will attack there, and the chlorine will attach to that carbon. Okay. Well, so far in our exploration of these things, we haven't created any chiral centers. You'll notice that in all of these previous molecules, the carbon that had the halogen on it had two of the same groups bonded to it. So for example, in this case, in our first one, you had two ethyl groups bonded to that. In our second one, there were two hydrogens bonded here. In our third one, the going around the ring on each side was the same. And that's also true for this most recent one. You have it going around the ring, one side and the other side is the same. So we didn't create any chiral centers up until now. And that's going to change in E. So we're going to go through the same procedure, but we have to also think about the chirality of this. Okay. Chirality of what the products will be. Well, what do we see in the recipe? We see an alkene. So already you should be thinking addition reaction. And then you think, okay, what am I adding? You have H and X. So a hydrogen and a halogen. So we're going to be doing hydrohalogenation. We do not see peroxides. That means that this is going to be Markovnikov addition. The hydrogen will go to the less substituted position. So I'm going to redraw the carbon skeleton exactly as it is, just without the pi bond. We're going to use those pi electrons to stick these new things on the molecule. Okay, well, because it's Markovnikov addition, we know that the hydrogen will add to the less substituted position. The carbon on the right is only bonded to one other carbon, so it's primary. The carbon on the left is bonded to two other carbons, so it is secondary. So the right position is the less substituted position. That's where the hydrogen will add in this Markovnikov addition. Now next we have this carbocation. It's on a secondary carbon, so a secondary carbocation. Next door you have a primary position and a secondary position. Neither of those are more stable than where it already is, so it does not rearrange. But if you think about this, okay, so it doesn't rearrange. So that's where the other group, the iodine, is going to add. So we'll put that iodine there. But if you look at that, you'll notice that the carbon that we have the iodine on is a chiral center. This carbon is a chiral center. It is bonded on one hand to an iodine. It's bonded to a sort of propyl group. It's bonded to a methyl group. And the fourth thing is a hydrogen, an implied hydrogen. And because we have a chiral center, we have to say what configuration the chiral center is. Is it R or is it S? And for you to understand which configuration we're going to get, you have to think back to the mechanism. So if you don't feel comfortable with the mechanism, go back to those videos and see what you get. You get that carbocation intermediate. Well, a carbocation is trigonal planar. That carbon with the positive charge is bonded to 3 atoms and has 0 lone pairs. So it's trigonal planar. It's flat. Because it's flat, a nucleophile can either attack from the top or the bottom. When it attacks from the top, it'll create one chiral center, and if it attacks from the bottom, it'll create the opposite chiral center. Because the molecule is flat, there's no preference, and you get a 50-50 mixture of the two. So, what we're going to do is draw both of them. So we're going to draw both of those two chiral centers. So one, where the iodine comes out at us, let's say it attacked from the top, and that pushed the hydrogen away. And a second one where the iodine is going away from you. Let's say it attacked from the bottom, and that pushes the hydrogen up. And so those are both, you get a racemic mixture, a 50-50 mixture of those two compounds in this hydrohalogenation. Okay. So next, we see an alkene, we see a double bond, and so instantly our mind should think addition reaction. That's what we can do with that. And then you look, okay, what am I adding? Let me look at the recipe. We see a hydrogen and a halogen, so definitely hydrohalogenation. But then you see another thing. You see a peroxide, 2 oxygens bonded together. So this is going to be anti-Markovnikov addition of H and Br. Anti-Markovnikov means that the hydrogen goes to the more substituted carbon. Well, if we think about these 2 carbons in this double bond, the carbon on the left is bonded to 1, 2, 3 carbons, so it is tertiary. The carbon on the right is bonded to 1, 2 other carbons, so it is secondary. Well, because we're doing anti-Markovnikov addition, the hydrogen will go to the more substituted tertiary carbon. But we know when we're doing hydrohalogenation, the sigma bonds don't change, it's just the pi bond that gets used. Those electrons get used to stick a new thing on the molecule. So we can still draw in all the sigma bonds. But now, the hydrogen will go on the more substituted carbon, because it's anti-Markovnikov addition. When we use peroxides, the mechanism is not the same as when we don't. So you don't have to worry about rearrangement, and the other group, here the bromine, will add on the other carbon in the double bond, always. And so that is our product. And you'll notice we don't have a chiral center there. Okay, so in this exercise, you saw how to, just from the perspective of synthesis rather than of a mechanism, how to draw a product quickly when you're just given the reagents for hydrohalogenation. You have to worry about Markovnikov addition and anti-Markovnikov addition. It'll be anti-Markovnikov only if you have a peroxide. You have to worry about rearrangement, so always think about the carbocation that's formed after you add the hydrogen and whether it can rearrange. And you have to think about chirality. So in this case, if you form a chiral center, you end up getting both of the enantiomers, a 50-50 mixture of the 2 enantiomers. And that's how you can think through these hydrohalogenation synthesis exercises.